Hello, the internet, and welcome to Open Source Directions, hosted by Quansight, the webinar that brings you all of the news about your favorite open source projects. My name is Anthony Skopatz, your host for Open Source Directions. Co-hosting with me today is David Charbonneau.
Hi, I'm David Charbonneau, and I'm excited to be co-host for this episode of Open Source Directions. I lead the development of open teams at Quansight, and I'm based in Durham, North Carolina.
And I'm Aaron Muir. I'm the lead developer of the SymPy project. I'm currently based in Albuquerque, New Mexico, and I'm happy to be here.
Excellent. This week, we are introducing a new section called Tweet of the Week, where each of our panelists presents a tweet that they have been enjoying recently. Aaron, you're the first up here today.
So my tweet is sort of basically a sort of cheating, because it's actually just a link to a blog post, but it's it's a very interesting blog post on the recent developments on Michael Attia's attempted proof of the Riemann hypothesis, and sort of what the author, it's from this blog by R.J. Lipton called hold on a sec. Called Gödel's Lost Letter and P equals NP, it's an excellent math blog, and this post sort of details what they think Attia is trying to do. So I think sort of the consensus right now is that his proof probably isn't going to work, but it's still very interesting. Sort of this idea of basically this Todd trick that they're talking about, and it'd be interesting if it could work, even if Attia's specific attempt at it doesn't work.
Very cool. David, do you have a tweet you'd like to share?
I do. I just now changed my mind because there was a really interesting one that came up this morning. I don't know if you're familiar with something called Fermat's library, but they provide a set of tools and a newsletter where they send you interesting papers from a variety of disciplines. But they announced a really cool thing. I'm going to paste the tweet into the chat here. They announced something called margins. So it's a tool where you can upload all the papers that you're reading or reviewing, kind of like your personal notebook, but it's hosted in the cloud, and you can annotate it and you can share your annotations and things. It just looks really, really cool.
Very cool. Sounds interesting. For my part, Conda Forge says that they are planning on stopping new Python 3.5 builds by default after October 1st. To please let them know if this is problematic for you or affects you in any way. And this is kind of consistent with their policy of only building 2 versions of Python 3. So those are 3.6 and 2.7. All right. Well, now that we've done our news section as it is, let's go ahead and jump into the actual meat of the episode. So today we're going to be starting by introducing SymPy. SymPy has about 5,100 stars on GitHub and was downloaded from PyPy about 190,000 times last month. And so David and I are just going to now ask a few questions about SymPy, and Aaron, if that's fine, you'll go ahead and answer. So, David.
Aaron, why was this project started?
Yeah, so it wasn't started by me. It was started by a guy called Andrei Chertek back in 2005, and basically he needed some of the ability to work with symbolics in Python with his work as a physics graduate student, and sort of basically he put it out there, and different people came in and contributed things that they needed, and it sort of kind of grew into a full-featured thing.
Cool. So what need does SymPy really fill in kind of the ecosystem of scientific software?
Yeah, so SymPy sort of fills the slot of symbolic computation in the scientific Python ecosystem. So most libraries in the ecosystem work with numerics, but SymPy works with symbolics, it's a very powerful thing, because virtually any field that deals with mathematical expressions, a symbolic system makes it so the computer actually knows the mathematics of what's being computed and can manipulate things algebraically and have a very high level understanding of the mathematics of your problem.
Are there
Very
any
cool.
are there any alternative projects out there?
So there are some popular proprietary systems like Maple and Mathematica, which they have very expensive licenses and they're closed source, so it's often quite difficult to understand how they work. And they also, they work outside of the Python ecosystem as well. Inside of Python, it's mainly just SymPy in terms of what's out there. There's also Sage, which sort of works in Python but pulls together lots of other things, including SymPy. And sort of one of the things that makes SymPy unique from its alternatives is that it's sort of designed to be used as a library. So in addition to being able to work interactively like a calculator, it can also be like you can import SymPy within your code, and there are other libraries that depend on SymPy as a dependency and use it completely programmatically.
Yeah, that programmatic aspect is, like, at least in my experience, has been very, very useful for SymPy for doing things with it downstream. So what technologies is SymPy actually built on?
Yeah, so SymPy is actually completely pure Python, and it has one dependency, which is mpmath, which is a pure Python library for arbitrary precision numerics.
Well, who maintains the project?
So right now I'm the lead maintainer. We have about a dozen people who regularly review pull requests and have push access to the repository, and we have lots of smaller contributors who contribute maybe once a year, once every few months, and in total throughout its history, over 750 people have contributed something to the project, at least one patch.
That's fantastic.
Yeah, very cool. Long-running project. So, what are the communities that the users and these contributors, which communities do these users and contributors actually come from? Are they coming mostly from the scientific Python, PyData stack, or are they coming from Sage, or where are people? How are you interacting with folks?
Yeah, I'd say mostly from sort of scientific Python world. I think most people who are using SymPy are also very likely to be using other parts of the scientific stack, like NumPy or SciPy or whatever. There's a whole slew of libraries that build on top of the stack. But I'd say a large chunk of the users are academic researchers, and from a whole variety of fields, because, like I said, SymPy is very applicable to any domain where you use mathematics, basically. And SymPy is very helpful to help people model their domain-specific problems. And and a lot of the contributions to SymPy have come from people just using it to solve their problem and contributing back something to help it work better.
Awesome. The way open source should work, right? So,
Absolutely.
Yeah. So I believe you have a demo / walkthrough for us, so that we can get a little bit better of a sense of what SymPy's capabilities are, rather than just talking about it. So here we'll maximize this demo screen that you've got up, and I'll paste.
Yeah. So I've got this Jupyter notebook here, and I'm just gonna do from SymPy import star here, and we also have this thing called init printing that basically it makes it so that when you type a SymPy expression in the notebook, it renders as LaTeX, which you'll see later.
Yeah, that's cool.
And so the first thing I just want to clarify what I mean by symbolic computation. So if I import the math from just the standard library math that comes with Python, and I do, say, for instance, math.square root of 8, that's just going to give me this number back. You can see it's rendering as LaTeX, but it's just a number. And so the difference here is with SymPy, if I do SymPy.square root of 8, because 8's not a perfect square, it's going to actually evaluate this exactly, and so it knows that 8 is 2 times the square root of 2, and so and of course things get really powerful because you can define symbolic variables called symbols, and so I can do like the square root of x, and that'll just be an unevaluated expression, square root of x. And so some of the sorts, just sort of a just sort of a some examples of the sorts of things that are possible with symbolic computation. You can do symbolic derivatives. Those are pretty easy. Symbolic integrals are more difficult than symbolic derivatives. But so, for example, I can integrate this expression that we just computed, and we should get the sine x times e to the x back. I can say, for example, integrate sine of x squared. I can do like definite integrals too. So actually, let's do like so like I can do say an unevaluated integral. That's just a symbolic integral, and then I can tell SymPy.
Are those two little o's? Is that what that is? Is that like a
yeah?
symbol?
So the I think SymPy borrowed this from Sage maybe or somewhere else, but yeah, infinity. The symbol for infinity is just two O's, which if you look at it, you can see the infinity symbol there.
Yeah. If you squint enough.
Yeah, but it's useful to have just a 2-character thing to type for infinity because it's pretty common.
Sure.
Yeah. Right, and so you can solve symbolic equations, for instance. So solve the equation x squared minus 2. There's symbolic matrices. So say I just take some random matrix here, and so now I can take, for instance, the eigenvalues of this matrix, and those are also represented symbolically as well.
So all these linear algebra operations then have a symbolic representation too, and symbolic algorithms for them.
Yeah, so everything in SymPy works symbolically. So I could even put like a variable in this matrix, and I could even put a variable in this matrix, and it would work symbolically with the variable as well.
Wow.
So everything, yeah. And another powerful thing that that I wanted to show off because it's kind of new. Well, so matrix expressions are not new. We've had these for a while. So for example, you can define A as just a symbolic n by n matrix, where n is just a symbol, and say, for example, take the trace of A squared. But the thing that's new is we're starting to get support for taking derivatives of matrix expressions with respect to matrices, which has been a very popular feature request that we've had for a while.
Wow.
So the derivative of the trace of A squared with respect to A is 2 times A transform. And then the final, well, actually, no, not the final thing. So another thing that is very commonly used in SymPy is cogeneration. So I'm just going to make this expression here, just the absolute value of sine of pi x. And so cogeneration just means I take the SymPy expression and I generate code for various language. So here's the C version of this expression. Here's the Fortran version of this expression. Here's JavaScript.
Wow.
That's very handy because you can do your experimental kind of, you can explore the space using SymPy, and then if you have a need for speed, generate the code without having to figure out how to handwrite it yourself.
Yeah, so
that's great.
Sort of the general workflow with cogeneration, is you sort of model your problem with SymPy and you use all of its capabilities to do symbolic derivatives or equation solving or whatever, and then once you have the thing you're trying to compute, you generate fast code for that actually numerically computes it using C or Fortran or whatever language you're targeting.
And it generates JavaScript as well. So
yeah, so we pretty much any language you can think of. These are just 3 that I sort of picked out of the hat, but we there's like a dozen languages. We have Julia, Mathematica, obviously C, C++, Fortran, JavaScript. I'm trying to think of which other ones off the top of my head. Pretty much any language, and it's also, we also have a framework where it's really easy to extend it if something's not supported for the language that your favorite language.
Yeah, that's awesome. It's really great to see this kind of abstraction available. So, all right. Well, is there anything else you wanted to share in this demo section?
Just one last thing is I just want to show that if you do the other way to go to back to the numerics is this lambdify function, which basically takes an expression and turns it into a NumPy function. So if I do import NumPy as MP and say A is NumPy dot. So I've just taken this expression and turned it in. This func is now a NumPy version of that expression. So if I evaluate it on a NumPy array, it'll evaluate. And so let me just copy paste this to make it easy. And so, for example, I can now use matplotlib to very easily show you what that looks like, just plotting these two NumPy arrays. And of course, SymPy also supports plotting as well. If you just want to do plotting and you don't want to worry about the NumPy stuff, but this ability to go from SymPy to NumPy or SymPy to C or SymPy to whatever is one of the most powerful things about SymPy.
Yeah, that's awesome. Are there ways to ingest other languages? Like, can you take in like LaTeX expressions as SymPy and then convert them to?
Yeah, so we actually have
symbols?
a new feature very recently added. It's a LaTeX parser. Basically, you can. Let's see if I can remember.
Yeah, sorry to put you on the spot a bit here. You just were saying there's all these ways to go from SymPy to something else. I was wondering.
Yeah, so I remembered the import correctly. It requires the Antler Python runtime, but it's very easy to install with Conda. So let's say so you know I can. It's pretty easy to go to LaTeX with the LaTeX function, and so.
LaTeX, the most beautiful language.
Yeah, and so for example, this is the LaTeX version of our expression. Just to remind, this is what our expression is right here. And so hopefully, if I pass this to the parts LaTeX function, this is still experimental, by the way, and it looks like there's a bug. It doesn't support these left-right things very well. Which is why it's still experimental. But I think if I delete those, it should work.
Got pretty close.
Yeah.
Oh yeah! Wow, look at that.
So check if that's the original expression, and it looks like it's not. So I don't know what happened. Like I said, it's experimental.
So looking for
Still
pull
cool.
requests. Yeah, it's still
Exactly.
a cool idea. So I guess since we're on this, since we're on the demo, Juan asks if Lambdify is as efficient as using NumPy ufuncs directly.
So Lambdify basically, it's basically just going to generate a function that. So here's my function. And this is actually a new feature that we've got. You can now do the double question marks. Lambdify, it literally just generates this function right here. But the trick is that abs, sine, and pi are the NumPy versions of those. And so this is going to be just as efficient as a Python version. We do have a function called ufuncify, which I think you might have to import it from somewhere. AutoRad.
It's not a 70s disco band.
Yeah, so ufuncify. Let's see if this works. So let's say ufunc. What ufuncify is going to do is it's going to actually create C code or Fortran code, depending on which flag or Python I think you can do as well, and actually go in and compile it and then import it. And so it's going to create a very fast, basically, ufunc from C.
So you have to have a compiler available.
Yeah, so you do have to have a compiler available, but you know, I imagine if I do time it on ufunc here versus time it on func, the ufunc will be faster, simply because it's actually creating an extension module. Yeah, so you can see that this ufunc is now
It's about 40%.
10 times.
Yeah.
Yeah. So, and this is under the hood. This is using this code generation to basically generate code and then wrap it in a nice extension module template and then generate a ufunc. But it's all done automatically for you as long as you have a compiler installed.
That's awesome.
Yeah, very cool.
All
you
right,
can also another thing is you can do numba.jit on these functions, and that on just a lambda5 function, and that makes it faster as well.
Oh, awesome. Yeah, so there's multiple ways to get speedups on the generated code here. So I think at this point, thank you for the demo, and we'll transition to our roadmap discussion. So this is, again, kind of the meat of the episode. Here's where we're going to talk about not just what the project is and what the project is doing right now, but where the project is going overall. And SymPy has a roadmap that you can see either on the SymPy homepage in the documentation, or it's also a brochure is available at quansight.com/project, so you can feel free to look at it there. But we'll go through and hopefully we'll hit the top few items in the roadmap and kind of dig into them a bit. So let's start with the assumptions system. Can you tell us a bit about the assumption system and where people can get involved, either via by contributing code or by funding the project and funding specifically improvements to the assumption system?
Yeah, so the assumption system, maybe I shouldn't have disabled screen share because I think it would be probably easiest to just show a simple example of what that means.
If you want to bring it back up, yeah, that's fine. If you think it'll work.
It should work, yeah.
Oh, okay, there we go.
This is the right notebook, right? Yes. Okay, so the assumption system is basically, for example, if I do the square root of x squared, by default, SymPy just assumes everything is complex, and so for a general complex number, this expression right here doesn't simplify at all because x could be, say, negative, or it could be imaginary or whatever. But if I instead say x is positive, and then I do this, then now it's going to simplify, because for positive numbers, the square root of x squared is just equal to x. And so the assumption system, you can sort of see here how it becomes important for even this very simple expression, and it sort of permeates like the entire code base, because basically in order to ensure correctness, you have to check for assumptions in all over the place, because we never want to perform a mathematical operation that could be invalid even for like a certain subset of possibilities. And so basically what I just showed you is what we call our old assumptions, where you just define an assumption on symbol. We also have these what are called new assumptions, where instead of defining it on a symbol, you just create these objects that can apply to sort of any expression. And so I can do, for instance, the equivalent would be, actually, let me redefine x so that it doesn't have these old assumptions. So I think the equivalent would be this, the new assumptions. And so the reason this is more powerful is because instead of just a symbol here, we can put any expression. And so the problem, like I said, is this permeates the whole code base, so it's very difficult to refactor the assumption system in even simple ways, because one change could affect, any of the like 10,000 lines of codes that SymPy has. And so it's a very challenging task to sort of go in and fix this, but our end goal is to sort of make this new system as powerful or even more powerful than the old system, and also as performant. And sort of, I'd say the biggest blocker on that is just development time, which funding could certainly help, because I think it's one of those problems that you really need a full-time developer to sit down and look at for, I don't know, maybe 6 months or a year to even make some progress on it.
Wow. So that's a pretty big ask. But is the idea that then the old system goes away, or that just everything?
So we've had sort of a
different use cases.
Yeah,
really.
we've had sort of an evolving view on this as they developed, and the current view is that the best outcome would be is if they sort of were merged together, and so they both sort of understood each other. So both syntaxes would remain, but right now, actually, this new assumptions is using completely different code than what this old assumptions is using. So there's a lot of duplication of work.
I see.
And things like that. And so that there's been some work to sort of try to make it so I think right now the new assumptions can read the old assumptions, but not the other way around. And yeah, it's kind of it definitely needs work, but.
So it looks like in both of these cases, I may be misunderstanding, we're fine, but you build up a set of assumptions that apply across some number of expressions. Is there a way to kind of try to evaluate within different sets of assumptions? In one case you assume X is positive, in another case you assume X may or may not be positive, for example?
Yeah, well, so I guess that another difference with these new assumptions is the assumptions are separate from the symbol. So with the old way, the assumptions are on the symbol itself. So if I do this, then X is positive. For
always positive.
Always,
then.
yeah. And so whereas with this, it's only positive like in this function call because I told it it's positive in this function call.
Got it. So you could define different scenarios and evaluate them over the same expression. Very cool.
Yeah. And the other thing that's sort of possible with the new assumptions, or that's sort of easier to do with the new assumption, is this deduction. So I can say like, don't want to do tab completion. Oh, it does work. Okay. Oops. So I can say, given that X and Y are positive, is X times Y positive? And that's true. And this sort of deduction is actually critical for the assumption system, because you often only know your base rules, like say some symbol is positive, and you want to build that out to a larger expression to know what its assumptions are. And so the deduction for these new assumptions is potentially much more powerful than with the old one, simply because we can sort of represent arbitrary Boolean expressions on them with these Q objects.
Yeah. Interesting. David, did you have something else you wanted to bring up on the assumptions here?
No, I was going to see if we wanted to move on to the next roadmap item.
Yeah, let's do it.
So the next one we have on the list is code generation. So what are the improvements that you're looking to do for code generation, and where are there specific places people could pitch in?
Yeah, so code generation, I kind of already showed what that was and talked about it. Basically taking SymPy expressions and generating C or Fortran or whatever language you want from that expression. And so I guess I discussed that there's sort of this pipeline of like, you start with your high level representation of the expression and work in SymPy, and then you use code generation to go down to your numeric code. And so basically we want to make that pipeline as seamless as possible. Right now, there's a lot of work that you have to do often sort of in between. And so that the ideal situation is you would just sort of tell SymPy in a very high level way what you want to do, and the code generation would work out what you need. And
Okay.
there's also other cool things you can do, like make these mathematical optimizations. So SymPy knows the mathematics of your expressions, and it can make optimizations potentially that are much smarter than what any compiler would be able to do, because compilers only have very limited knowledge of the mathematics.
Mm-hmm.
And
so these are things like beyond common subexpression elimination, right?
Right. So common subexpression elimination is there, and compilers can do that as well, and
right.
But things like, for example, I guess I didn't show, but simplification is one of the things that SymPy can do fairly well.
Did you want to show it?
Yeah, it's still screen sharing here. Yeah, so for example, SymPy knows that sine squared x plus cosine squared x is 1. And so if you somehow generated code that had that expression, which it is not unreasonable to assume that would happen, because often the code that ends up being generated is sort of many layers of separation away from where you started, just because things are automated by SymPy. SymPy could potentially simplify this and generate. Obviously, it's much faster to evaluate 1 than it is to evaluate sine x squared plus cosine x squared.
Right. Yeah. No, those kinds of improvements would be really interesting to implement, I think, from sort of an optimization pipeline standpoint, and are sort of unexplored in a lot of senses.
Yeah.
The next big roadmap item where people can potentially contribute are by either jumping in and helping code or via funding is performance. Does SymPy have big issues with performance, and what are those? And can you speak a little about some of the ongoing efforts to that?
Yeah, so as I mentioned, SymPy is written entirely in Python. It's pure Python. And so often that can make it slower than what we would like. And so basically this roadmap item is to sort of go through and improve performance however we can. And there are sort of many different avenues we can approach that. One way is to sort of benchmark and profile and try to find things that are done inefficiently and fix them. And another way is to sort of find sort of faster algorithms to do some of the symbolic operations.
Right.
And then another approach that's being looked at is there's this SymEngine project, which is a very fast symbolic just core library that's written in C++. And so which was also started by Andrei Chertek, the guy who started SymPy. And the idea is to sort of make it so that the core of SymPy can be swapped out for SymEngine if it's installed, and that would make everything inside of SymPy faster because it's being run on this symbolic, C++ core.
Awesome. So in some sense, the SymPy roadmap kind of includes the SymEngine roadmap in a way, or at least making.
Yeah.
SymPy
Well, so
specific
SymEngine. It's a sort of an independent project as well. So, and it has backends to various languages. So I'd say the SymPy specific part of that is to sort of make SymEngine make a core for SymPy with SymEngine that can be used inside of SymPy itself.
Kind of make it so that people can use SymEngine, but using the SymPy API that they're comfortable with and used to.
Exactly, and also SymPy has tons and tons of symbolic algorithms that are basically out of scope for SymEngine, because SymEngine's just focused on making a fast core, and so you could sort of get the best of both worlds if you could use fast SymEngine expressions, but still get like the powerful, say, integration algorithms that are in SymPy.
Awesome. So the next roadmap item is SymPy Live and SymPy Gamma. So could you just explain, or maybe even perhaps show what those are?
Yeah, I'll just show.
This window here.
If you go to our website and go to this online shell, it's live.symp.org. live.sympy.org. Oh, and apparently it's just showing the mobile site because I have my window too small. So let me hopefully, there we go. Oh, that's why I was doing it, because I had my font size too big. Yeah, so SymPy Live is, you just go to the live.sympy.org, and it's a shell in your browser that has SymPy in it. And so you can see these commands have already been run, and I can type code, and it's just like a Python shell with SymPy. And this is also integrated into our documentation. So if you go to our documentation and say, go to here, if you click on one of these things, any of these code blocks in our tutorial, it'll take that code and execute it in the shell. And then you can go in here and sort of play around with it, and see what happens if I change this in there.
And it does the rendering of the LaTeX right there in the browser too, it seems.
Yes. So this is using MathJax, the same thing that it uses in the IPython notebook, or the Jupyter notebook.
Old habits die hard.
It's still IPython in my heart. No, but and so that this works, but it's sort of the live shell. It can use a lot of improvements, especially in the back end. Right now, it's sort of it's written using the Google App Engine.
I see. Okay.
And the App Engine isn't really designed for applications like this. Like this isn't really a persistent this. Like if I do A equals 1 and then A, it acts like it's a persistent shell, but it isn't really. It sort of fakes it. And so it would be better to move this to a more modern backend, and it would also be better to improve the front end as well. But the biggest hurdle here is that myself and most of the developers in SymPy aren't web developers, neither backend nor front end. So it's very difficult for us to make improvements to this.
Right. Yeah. No, this is something that's really cool. It'd be great to see this kind of thing available for a lot of different projects.
Yeah, and so it'd be great. It'd be great if we could sort of split this out and make it general to something that other projects could use as well. Because I know, this interactive thing that you can do in our docs is very nice, and it'd be great for any project to have that sort of thing.
Right. So if you're interested in working on or funding that, just get in touch with Aaron.
And then SymPy Gamma. If you go to Gamma, well, even on our website, if you click on, for example, up on the top right, it's basically our version of Wolfram Alpha. You can type an expression in here, and it'll compute various things. So here it's computing some integral. And so, for example, I guess this is not a good example for what I want to show. And so, for example, here's an integral, and it's going to plot it and take the derivative, and here's the steps to compute the step-by-step steps to compute the integral. And so, but at the same problem as before, it'd be great to improve this and make it be able to compute more things, and maybe add some better natural language processing like Wolfram Alpha has, because right now it's has very sort of limited extensions to Python syntax. Like you can do 2x instead of 2 times x, but you can't do sort of the natural language stuff that Wolfram Alpha allows. And but like I said, and the back end of this is also on the App Engine, which would be, I don't know if it'd probably be better to move to something better.
Awesome. Yeah, no, that's a really cool feature to have. I think we'll wrap up our section here on the roadmap. But if anyone, just like there's a couple extra sections on algorithmic improvements and general improvements that you can read about at quansight.com/projects or on the SymPy roadmap on the website. But is there anything else specifically or quickly that you wanted to mention, Aaron, or is this?
I would just mention for our roadmap that sort of the broad scope of SymPy is sort of anything, any sort of symbolic computation is in scope for symbolic mathematical computation is in scope for SymPy. So there are a lot of things that we would like to have implemented that aren't on the roadmap specifically, but they're definitely in scope. And if it's in scope, we'd love to have it.
Awesome. Yeah. It's a huge project with a lot of goals. So, all right. So at this point, we'll go ahead and move to our user question section. And so we've actually had quite a number of questions from the audience today and previously on Twitter, etc. So for our first question today, Saul Shinabrook asks, are there any thoughts on if and how MatchPy, used in a previous Google Summer of Code for Ruby integration, can be useful to SymPy?
Yeah, so for those who don't know, Ruby is a mathematical library that does symbolic integration basically by having a very large table of integrals, and then it uses Mathematica's pattern matching abilities to sort of match the input to the table and produce an output. And so that the goal for, I think the past 3 years, various Google Summer Code projects has been to port this to SymPy. And the MatchPy library has been very helpful with that. So right now we're sort of seeing it, if how MatchPy can be useful for Ruby, and if it ends up being powerful, we could maybe use it for other things. I think one of the challenges right now with MatchPy is finding someone to maintain it and to work on it. I think the person who started it has moved on, but and I think there are a few things that need to be implemented in it. So I think one of our Google Summer of Code ideas for next year is going to be to improve MatchPy.
Very cool.
Well, the next question we have here says, DXLI asks, I need to evaluate a SymPy lambda function in parallel using multiprocessing.pool. Is there a way that the SymPy lambda function could be pickled by default to work when used in pool?
Yeah, so I haven't actually tested the pickling recently. I don't know if I still have screen share enabled.
You do. Yeah.
Okay. Well, so we did recently refactor Lambdafy a little bit, like I showed. What was it? Like I showed here, Lambdafy doesn't actually generate a lambda function anymore. It generates a real function. So that might actually help with the pickling, but it's something that I haven't tested, so I can't say for sure. The one thing I will say, or the one thing I would suggest is to, if it doesn't work, then to just basically recreate the lambda function in each pool instead of trying to pickle it, because the creation of the lambda function isn't the slow part; it's the evaluation. So it shouldn't be an issue performance-wise to just recreate it on each thread or each process.
Yeah, so kind of flip that a bit on its head, right? Is kind of the answer. Yeah, cool. Rastapopoulos asks, is there a canonical way of declaring a function by parts in SymPy?
Yeah, so I'm not sure I fully understand the question, but SymPy expressions are Python objects. So, for example, you can assign them to Python variables. Like I assign this object, this expression here, to this Python variable, and so you can build an expression by parts just by assigning to different Python variables, and then I can do say the Python variable a is x squared, and the Python variable b is 2 times x, and then if I do a plus b, it'll give me x squared plus 2 times x. So you can build up an expression by parts just by assigning it to variables and then combining those variables, I would say.
PCU asks, is there a robust way of finding functional parameters in a SymPy expression?
I'm also not sure if I understand this, but if I understand the question correctly, you're trying to find the variables in an expression, and the best way to do that is to use the free symbols attribute. It'll give you a set of all the variables in the expression. So if I have, like, say, x times y, so it would just be like your expression dot free underscore symbols. If I'm understanding the question.
Okay. For the next one up, Juan asks, I would love to know about the status of the new style assumptions and if there's a planned effort to systematically go over the wrong result tag on GitHub. So this is a little maybe in the weeds for our for relative to the roadmap discussion, but
yeah. Well, the first part is on a roadmap, and I discussed that earlier. And the status is basically I would consider the new assumptions to still be somewhat experimental. I would recommend using the old assumptions for whatever you're trying to do, unless you're willing to try out the new assumptions experimentally. And then the wrong result tag, I would say there hasn't been any plans to do that, but I think it would be a good idea. We definitely need to go through our issue tracker in general and try to triage it.
Michael Eaton asks, yeah, that's what was going through my head. Michael Eaton asks, have any security reviews been done on SymPy?
Not to my knowledge. SymPy doesn't, for the most part, doesn't have security implications. Although there is one thing I will say is we have a function called simplify, which basically takes a string and turns it into a SymPy expression. And I would recommend being very careful with this function if you use it against untrusted input, because it uses the eval Python construct underneath, so it's unsecure basically. And there have been I've looked at trying to sort of make it a little safer by default, but that work has not been finished yet.
Just run everything in a Docker container, right? That's the end. Juan Cano asks one last question for you, Juan. SymPy is growing a lot in feature surface. For instance, the physics package, right? So there's subdomain packages inside of SymPy. Have you ever considered splitting it into packages? You talk a little bit.
Yeah.
About that.
So there have been discussions about that with the physics package. It's not there are some submodules that it would be very difficult to do that because SymPy is very tightly linked, but the physics package is more separated than the others. There aren't any parts of SymPy that depend on physics. It's mainly the other way around. And so far, the consensus has been that if the code is in SymPy, then it sort of gets all the maintenance that SymPy gets by default. So, for example, every time somebody opens a pull request on SymPy, the entire test suite is run on Travis, which includes the physics test. So even if it's a change that's not to the physics module, but maybe inadvertently breaks one of the physics module tests, then that'll be seen immediately. Whereas if it were a separate package, that it might not get as much maintenance love. But there, it's if somebody is willing to become a maintainer for one of the sub packages and wants to pull it out, I would definitely be open to
that. Michael Cotty asks, are graph algorithms implemented in SymPy so that they always return symbolic expressions, like graph algorithms in Mathematica do?
Well, so I'm not entirely sure what the question is asking. We don't have any graph theory in SymPy.
Yeah, I think that's what this was kind of driving at. Like, can you find sort of a path through a graph symbolically and things like that?
Right. So
So if you have a DAG, is there a way to represent a DAG symbolically, and what?
right. So if you want to represent a graph, I would recommend using like Network X or a library like that. We've sort of considered graph theory to be out of scope for SymPy because it's already implemented in these other libraries, and it doesn't particularly tie into other symbolic parts of SymPy, where it wouldn't need SymPy. And if somebody, if you could demonstrate that that's not the case, then I'd be open to changing that. But,
You can attach a SymPy expression to a network X graph, if I'm not mistaken, right? So,
right, and so yeah, probably. I think network X graphs can contain arbitrary objects, if I'm not mistaken, as well.
Yeah, I think that's correct. So hopefully that gets you most of the way there, Michael. And if not, please open an issue, I would imagine. All right. So at this point, there are no further questions, and we will enter our world famous rant section. So each person gets a 15-second soapbox to rant on whatever topic we want. So Aaron, you're first up here as our special guest.
Okay. Yeah. So I think what I'm going to rant about today is because I saw something on Twitter that sort of reminded me about this, is that I've basically become convinced in the past couple of years that one-based indexing is better than zero-based indexing, but because unfortunately everybody's become basically radicalized one way or the other. It's impossible to sort of convince people either way. So I guess my rant might be just a meta rant that there even are different ways of doing it.
All right, David.
I forgot we had this section. It's been bothering me lately. No. I've got one. So occasionally, my system, my computer, just kind of becomes undiagnosably slow and jittery, and I keep rediscovering that it's Time Machine, and so I disconnect my USB hard drive and I reconnect it, and I would love it if it would just work and not like drag my system to a halt or make it behave like crazy, because it's necessary and it's valuable. But yeah, that's been driving me crazy. Is I finally figured out again for the 10th time this week that my machine was going slow because of Time Machine.
Funny. For my rant today, I love Conda. I love Conda Forge, but wow, is the solver so slow? And I just wish there was something that could be done about that. All right. Thanks, everybody. Thanks for watching. Thanks for listening. You can find us on Twitter at Quansight AI. If you're interested in funding open source projects, including SymPy, you can find all of the project roadmaps at quansight.com/projects. Aaron, where can people find you and SymPy?
Yeah, so I'm on Twitter under my username ASNeurer, ASNEURER, and also on GitHub under the same username. And SymPy is on Twitter and GitHub under username SymPy, and you can also go to our chat room on gitter.im/SymPy/SymPy, and that's open to both users and developers.
Great. David, where can folks find you?
I'm on GitHub with username dcharbon, DCHARBON, and I'm also on Twitter, but I talk about a lot of things, not just technical things there. So if you're interested in politics as well, then you can check that out.
Yeah. Join us again next episode for a lively discussion on PyViz. Thank you very much, everybody. See you again next time.
Thank you.